So welcome to lecture 11. So in the last class we had derived how the area element transforms, isn't it? And we got that Nancy formula that dA, the deformed area element, is equal to det F into F inverse transpose into dA naught. Okay. And if you want to also see how the normal to the area element transforms, then we can do the following. So from here, we already saw that this is same as NDA, where N is the surface normal. Okay, it is not the direction of the line element; it is the surface normal. That's equal to det F into F inverse transpose into N naught times dA naught, and dA naught is the scalar quantity, so I took it out. So remember, this is undeformed surface normal, whereas this is the deformed surface normal. Okay, so from here you can easily see that the deformed surface normal n, which is a unit vector, see the normals are always unit vector, so n is then going to be F inverse transpose n naught divided by mod of it. Okay, contrast this with the direction of the line element. How was the direction of line element transforming? Can you recall? So that was n equal to f n naught divided by mod of f n naught. So do not confuse that the two n's are same. Okay, this is the direction of line element, whereas this n is the surface normal. Can you guess why they are deforming or they are transforming in different ways? One through big F and whereas the other one through F inverse transpose. Surface normal is out of body. Well, no, you see the surface normal that we are talking about, that is at any point in the body. So here is the body, and I then look at a point in the body which did not be on the surface. It could be even within. Okay, and then within the body you have a point, and then you think of two line elements there that generates a surface, right? It's an internal surface of the body. So it can be internal surface as well as outer surface. Okay, normal is transformation of direction dA, and dA is transformation of vector and will need transpose. Well, no, we may say both will be normal to each other. Anyway, let me tell the answer. So the direction of line element. So line elements are something, which are actual material lines, whereas surface normal is not consisting of material particle. It's like a imaginary direction, surface normal, whereas line elements are real material lines. And so on the right, you have transformation of real material lines, whereas on the left, it's the transformation of what is called imaginary lines. Okay, so that's why they do not transform in the same way. All right, so we really derived a lot of formulas. We derived formula for longitudinal stretch at any point in the body. We derived formula for shear strain or change in angle between line elements at any point in the body. We derived formula for change in volume. We derived formula for change in surface area. We derived formula for change in surface normal. So lots of formulas. And they are all exact formulas. They are local first of all, which means the line elements or the surface elements or the volume elements, they are all infinitesimal. Therefore, they have local characteristic. Okay, just that. Otherwise, it is exact. All those formulas they hold for even large deformation. Even when the body is undergoing large deformation in whatever way possible, those formulas are going to hold. Okay, but you can recall that just few days ago I was saying that in undergraduate, for example, you don't you have a different formula. So we'll now like to derive that formula from our more exact formula. I mean from the exact formula, not more exact. It is exact. Okay. So let's begin with longitudinal stretch, for example. So I'll say approximation of longitudinal stretch formula. And we'll figure out what approximation is to be done. Okay, so recall that lambda was used to denote longitudinal stretch at any point and for a given line element. So we need two arguments here, x for the point and n for the direction of line element, right? And then this was equal to square root of f transpose f n naught or n dot with n, right? So that's the formula. And you can recall that your UG formula was obviously in terms of displacement gradient. So let us try to write this in terms of displacement. Okay. Now F, what is your F? This deformation gradient tensor is the gradient of the deformation map, which is gradient with respect to x of y hat, isn't it? But you also know, and from here you can actually say that Fij is equal to del yi hat over del xj, right? Now let us try to write this in terms of displacement. So do you recall that the deformed position y was equal to the reference position x plus displacement u, isn't it? So displacement was being measured relative to the reference position. Now take the, write down this in component form. This would mean yi is equal to xi plus ui, correct? Now take the derivative on both the sides. With respect to xj, so this gives me del yi over del xj, that's equal to del xi over del xj plus del ui over del xj. Now what is del xi over del xj? Derivative of ith coordinate with respect to jth coordinate. What is that going to be? That's simply Kronecker delta ij, right? Not 0, Kronecker delta ij. If I and j are same, then it is 1, otherwise it is 0. Okay, so that's Kronecker delta ij plus del ui over del xj. So that's the component form. And from here, can we write down what will be the tensor form? So del yi over del xj, for example, this is the ij component of the deformation gradient matrix, isn't it? So you can write this as ij component of the deformation gradient matrix, right? Delta ij, can we say that it is the ij component of identity matrix? Right? Identity matrix has a similar property, whereas the last one would then be the ij component of displacement gradient matrix, isn't it? So you see del ui over del xj is forming displacement gradient. Okay, it's a new quantity. But from here, since each of the components are related in this way, you can also say that deformation gradient tensor is equal to identity tensor plus displacement gradient tensor, isn't it? Okay, so you have a new tensor, displacement gradient, whose components are del ui over del xj. Okay, it's a matrix. Its representation is a matrix with its components being del ui over del xj. Okay, so let us get back to the formula. See, we wanted to write down this big F in terms of displacement gradient. So we have to use this formula. So we come back here and write it as identity plus grad u for big F, and then take its transpose. Okay, into again identity plus grad u. And remember that this grad is Lagrangian gradient with respect to big X times the normal of, sorry, times the direction of the line element n, and then you further dot with n. Okay, so this we can further write as, see, work out these multiplication, one tensor multiplied with another one. So you have to multiply in the usual way. First of all, you have to take the transpose of first one. So that is identity transpose is the identity itself, because identity is a symmetric tensor, right? Fact that it is diagonal means it is symmetric, plus grad u transpose, okay, times again identity plus grad u into n dot with n. You see, as of now, we haven't applied any approximation. This formula still holds for finite deformation, large deformation. Then let us multiply the two second order tensors here, and what you have is identity plus grad u plus grad u transpose plus grad u transpose into grad u. Okay, times the surface normal dotted with surface normal. All right, so even now the formulas are all exact, no approximation till now. Okay, now let us multiply with the norm, this n, the direction n. So what do we get then? This is square root n plus grad u plus grad u transpose times n, right? And then you further dot with n plus the remaining one. Okay, now again come back. You see n dot n. So this n dotted with n. What is that going to give you? N is the unit normal, right? So that gives you 1 plus grad u plus grad u transpose n dot with n. Okay, plus the remaining thing. As of now, we haven't discarded anything. Okay, now you see, do you remember from your undergraduate class what was the order of displacement gradient? Each of the derivatives, del u I over del xj, what was its order? Can you recall? For example, the formula for longitudinal strain epsilon xx, that was del u1 by del x1, isn't it? And how much strain were you talking about in your undergraduate class? Can you recall? Anybody, can you give an estimate? How much strain were you talking about in the undergraduate class? 3 to 5%. That is true. Well, sometimes even 1%. So that's the order of which we are talking about in undergraduate class. So you can say that this is of the order of point zero, let us say 3, if it is 3%. And this is with just one of the derivatives, del u1 by del x1, but in fact all the derivatives were of this order. You can say that all the derivatives, if you write del ui over del xj and take its mod, they were all of the order of 1% or 2%, 3%, something like that. Okay, even the shear strain was of the same order, and shear strain has del u1 by del x2 plus del u2 by del x1, and that was also of this order. So you can see that all the derivatives are of this order. Now, if that is the case, what do you think is going to happen to this term over here? So let's try to work that out. So grad u transpose into grad u. Suppose this is a tensor C, then what is Cij? Can anyone tell me what will be Cij? So if this were A and the other one was B, then Cij is Aik Bkj. But A is grad U transpose. So Aik is nothing but del uk over del xi. Okay, and Bkj is simply del uk over del xj. So that's your Cij. And you see it's a quadratic combination of the displacement gradient. It's quadratic combination, right? Now in undergraduate class, the gradient was of the order of 1%. What do you think this quadratic combination will be of the order of? What will be its order? If each of the terms are 1%, another one also then 1%. So 1% into 1% is what? 1% of 1%. What will that be? That's true, 0.01%. So you can see it is really small, no? That's even smaller. So that's why in your undergraduate class that is obviously neglected. But let us not do that right now. So this is just to give you a hint that this term is neglected in UG class. So let us come back here and continue with our derivation. Now you see this has got 1 plus grad u plus grad u transpose n dot n plus the higher order term, no? So I'll just write that as um, dot dot dot, or maybe I can say big O grad u square, right? You can say that. And then to the power half. Okay. Now you see the second term here is also very small compared to 1 because it is 1% or something like that for UG, not for for PG level courses. They can be significant, but in UG level, the second term is also very small. Third term, of course, is small, 0.01%, whereas the second term is 0.1%. Sorry, 1%. So from here, let us further come down and try to use binomial expansion. Do you remember binomial expansion? So 1 plus x to the power n. Do you remember? If x is much, much less than 1, then this is 1 plus nx, right? So let us try to do that. So you get lambda x n, that's equal to 1 plus half of grad u plus grad u transpose of n dot with n, okay, plus again the same big O grad u square. Can we write this? See, I didn't write the half here because half does not change the order. Okay, so it gets engulfed. So what is then epsilon? See, at this point you might think, why don't I neglect everything, because everything is negligible compared to 1. So why don't I neglect this as well as this, both, and say that it is 1? So yeah, that's a fair thing to think about, but only bad thing is that you have removed everything actually. The other thing is, once you have lambda like this, then what is your epsilon? Then epsilon of x comma n is simply lambda minus 1, right? Then that is 0. So although deformation is happening, you are getting epsilon to be 0. So we don't want to come to this situation. So therefore, we don't neglect the leading order term in U. So let's keep the leading order term in U, which is also the linear term in U. It is linear, right? Can you see that it is linear in U? And the other one was quadratic, right? So that's the most significant term. So this is the most significant term in U, displacement. Okay, and I want to keep that. So from then you notice epsilon of x comma n would then be approximately equal to half of grad u plus grad u transpose into n dot n. Okay, so this is what is the formula for epsilon that we use in undergraduate class. Can we recover that epsilon xx is del u1 by del x1 from here? So remember that in undergraduate epsilon 1 is del u1 by del x1. And what was epsilon 1? That is the elongation or the normal strain of a line element along E1, right? So we have to choose n to be E1 here. Okay. So choose n equal to E1 and see what we get. You see this formula that you have here, it's in tensor form. So why don't I try to write this in some coordinate system? And let us use E1, E2, E3 coordinate system. So if you do that, then what is half of grad u plus grad u transpose? What is that going to give you? So grad u is the displacement gradient matrix, grad u transpose is the transpose of displacement gradient matrix, and you have to add them and further divide by half. So on the diagonal, you have the usual thing, del u1 by del x1, del u2 by del x2, and del u3 by del x3. Okay, but on the off diagonal, you have half of del u1 by del x1, sorry, del x2 plus del u2 by del x1, and then this one is half of del u1 by del x3 plus del u3 by del x1, and this one is half of del u2 by del x3 plus del u3 by del x2. Okay, and then it is symmetric. Sorry, not this one. It's this one which comes here, and these two. symmetric, right? So that's the matrix of half of grad u plus grad u transpose. So you have to multiply with n and further dot with n. And if you take n equal to e1, let us see what we are getting. So this is half of grad u plus grad u transpose, okay? That's a matrix. So n equal to e1, that implies in the coordinate system of e1, e2, e3, n becomes a column and it's going to look like 1, 0, 0, right? So what is then epsilon? Is that this particular matrix multiplied with n, which is 1, 0, 0, okay? And then you, whatever you get, you dot that again with 1, 0, 0. So can you see what are you going to get from here? So this is del u1 by del x1, del u2 by del x2, del u3 by del x3, and then you have these terms. So you multiply this matrix with 1, 0, 0, you get the first column. You get the first column. And first column further dot with 1, 0, 0, you get this first entry here, which is simply del u1 by del x1. And see, this is what you had in your undergraduate class. Okay. Similarly, if you choose n equal to e2, that means 0, 1, 0, then you will find that epsilon 2, 2 is del u2 by del x2. So you recover your undergraduate class formula. Okay. But what you see is that your undergraduate formula neglects this quadratic term. Okay. So it assumes that the displacement gradients are very, very small, and therefore you are neglecting the quadratic and higher order terms in displacement gradient. Is that okay with everyone? Let's try to see the formula for shear strain. Can we recover that? So you remember that cos theta that we derived, that was um, can someone tell me what did we derive for cos theta? Okay, so I remember it now. So that was big F n naught 1 dot with big F n naught 2 for the two line elements divided by lambda 1 lambda 2. Okay. So this is then equal to, so here again you have F transpose F n naught 1 dot with n naught 2 and divided by lambda 1 lambda 2. All right, so you can again write this as F transpose F, write it in terms of displacement gradient, and you have I plus grad U plus grad U transpose plus grad u transpose grad u n naught 1 dot with n naught 2, all right, divided by lambda 1 lambda 2, which is, well, let it be as lambda 1 lambda 2 for now. Okay, so this further implies that cos theta. Now suppose that your original line elements, the two line elements, are perpendicular to each other, because that's what we do in undergraduate class, isn't it? So let n naught 1 be perpendicular to n naught 2. So we choose two perpendicular line elements and see by how much the angle between them has changed. So if that is the case, when you work out this thing, you get n naught 1 plus grad u plus grad u transpose n naught 1, and this thing you dot with n naught 2, okay, and then you have this higher order term, no, plus big O grad u square, okay. So I'm guessing everybody is with me, divided by lambda 1 lambda 2, okay. So let it still be as lambda 1 lambda 2, but now you see this n naught 1 and n naught 2 being perpendicular, the first term drops out. N naught 1 dot n naught 2 is then 0, and what you have is simply grad u plus grad u transpose n naught 1 dot with n naught 2, okay, plus this higher order term multiplied with lambda 1, or I should say lambda 1 inverse, yeah, lambda 1 inverse and lambda 2 inverse, okay. Now lambda 1 we had derived above. See, this is your lambda over here. So let's write that. So we are going quite slow, okay? And we are almost finishing. You have to see these steps thoroughly. You'll see how, this is not arbitrary thing. We are doing everything systematically. There is nothing arbitrariness when you divide some approximation. It is not arbitrary. Into lambda 1 inverse, so that is 1 plus, sorry, this was 1 plus grad u plus grad u transpose n naught 1 dot with n naught 1, right, plus again the higher order term in grad u square and this is to the power minus half. Okay, and then the last one for lambda 2 inverse. So that's 1 plus grad u plus grad u transpose n naught 1, sorry, n naught 2 dot with n naught 2 plus grad u square to the power minus half. Are you all with me? So let us take this minus half inside, and so it becomes, or we can do it here itself. So if we take this minus half inside, this 1 plus thing here, you get minus half, right? Likewise over here also you have minus half. Okay, and now we simply have to multiply. So let us see what will be the outcome of this multiplication. So have a look at this. This first term, this is going to get multiplied with 1 here and further with 1 here, right? And that's going to give you grad u plus grad u transpose times n naught 1 dot with n naught 2, isn't it? Then think of um, this term getting multiplied with 1 here and further getting multiplied with this second term over here. And what do you think? What are you going to have? Can you see, once you do this multiplication, the middle term is 1, but the first term is of the order grad u, linear in u, and the last term is also linear in u. So when you work out the multiplication, overall that is a quadratic term, isn't it? So overall it's a quadratic term. So in fact it turns out you work out all kind of combinations. Rest all are either quadratic or cubic or higher orders. Okay, so if that is the case, you can simply write it as plus big O grad u square. So that makes our life really easy. Okay, so this is your cos theta. So originally you had two perpendicular lines. One was n naught 1 and the other was n naught 2. And after deformation, it may have become like this. Okay, n1 and n2. And this angle is theta. But can you recall what was shear strain in UG class? Shear strain was 90 minus theta. That's the change in angle. Okay. So if gamma is your shear strain, then gamma is also equal to 90 minus theta, right? Or that means theta is equal to 90 minus gamma, with gamma being the shear strain. So come back here and write theta as 90 minus gamma. So cos of 90 minus gamma. So that means cos of 90 minus gamma is this grad u plus grad u transpose n naught 1 dotted with n naught 2, which is also same as sine of gamma, right? So here since I'm neglecting quadratic term, I'll say it is approximately equal to, or sine of gamma is approximately equal to, you see, there was no arbitrariness. We are just removing the quadratic term and retaining the most significant term in U. Okay, so that's a formula. And in UG class, as you recall that displacement gradients are like 1%. So sine of gamma, this formula that you have here is like 1%, 0.01. So sine gamma becomes same as gamma, right? So this also implies that gamma is almost equal to grad u plus grad u transpose of n naught 1 dot with n naught 2. Okay, and let us take, let n naught 1 be equal to e1 and n naught 2 be equal to e2. Okay, so I want to look at the angle between e1 and e2, shear strain, and see what formula we get from here. So this is a tensor formula. Let us write this in a coordinate system of e1, e2, e3. So grad u plus grad u transpose. So this matrix, we already know what this is, right? This is del u1 by del x1, del u2 by del x2, del u3 by del x3, and here you have del u1 by del x2 plus del u2 by del x1 and del u1 by del x3 plus del u3 by del x1, and likewise you have other ones. So you multiply this with n naught 1, which is e1 here, that's 1 0 0. Okay, after multiplication, the vector that you get, you have to dot it with e2, that is 0 1 0. And can you guys guess what is this going to give you? So it's going to give you this term over here, okay, which is same as this term over here, which is simply del u1 by del x2 plus del u2 by del x1. And isn't this the formula of shear strain that you learned in undergraduate class, right? So you just derived that, but you see, you derived it now mathematically, working out exactly. So perhaps you might like this, or this is just another approach, of course. Okay, likewise, you can find out the angle between E1 and E3, giving you shear strain gamma 1 3. Okay, and you'll see that it gives you whatever you had learned there. So, and Mahadevna is saying, you told transformation of deformed surface normal is imaginary. I didn't understand that part. Okay, so what I meant is that surface normal is not something through which you have material particles passing through. So when you track the deformation of a surface normal, you are not tracking material particles. Okay, because surface normal itself is an imaginary line. Surface is a material surface, so on surface you have particles, but normal to the surface is not a, a material line. So that means once the surface deforms, normal to a surface by construction has to always remain normal. But if there were a material line along the surface normal originally, then after deformation, that material line will not remain normal to the deformed surface, right? But the surface normal that we are talking about here, it always has to be perpendicular to the surface. So therefore, it's an imaginary line. So of course, the next question is, all the formulas that we have derived, why don't I work out its approximation, the leading order contribution to those formulas in terms of grad u. For the, for example, for volumetric strain, what is that going to give us? So I'll give that to you as an exercise to work out. Anyway, so have a good weekend, everyone. See you next week.